The last thing we need to talk about in Chapter 19 is about the strength of acids and bases and how can we tell the difference. So acids and bases are classified as strong or weak based on the degree to which they ionize in water. So that means when they break apart. Okay, so strong acids completely ionize in aqueous solution. So here we have an example of hydrochloric acid breaking down with water, and it makes hydronium and then the chloride ion. So there's no hydrochloric acid left, no HCl together, so we say that's completely ionized. The dissociation of a strong acid shows how when you're done, so this side is the done side, I guess you would say, the product side, after the reaction takes place, and it's showing how there's no acid left, just the hydronium and then the anion. So because a strong acid completely dissociates, the concentration of the hydronium ion is high in aqueous solutions of those strong acids. A weak acid, on the other hand, only slightly dissociates in solution. So if you look here, if this is the before, where we have all acid, and then the after, there is still some of that weak acid left. And so the H3O plus, the hydronium, and then the anion both have a lot lower concentration because the acid didn't break apart. So it only slightly dissociates, we say. And so it will remain mostly intact. So the concentration of the hydronium ion will be much lower. With bases, it's kind of the same way. A strong base will completely dissociate into its ions. So for example, the strong base we have here is sodium hydroxide, and when that breaks down, it makes the sodium ion and the hydroxide ion, which the hydroxide is kind of present, so that tells us it's a base. But then a weak base will react with water to form the conjugate acid of the base in hydroxide ions. So the amount of the dissociation is also really small for weak bases. So here we have ammonia with water, and ammonia acts as a weak base because it makes ammonium, which would be its conjugate acid, with hydroxide. So it doesn't break apart fully like the strong base would. Strong bases and ionic compounds usually contain cations from groups 1A and 2A, and the hydroxide as the anion. So for example, sodium hydroxide, potassium hydroxide, those are two very, very common ones, and then calcium hydroxide would be an example of a group 2A strong base. But a good rule to say is if it has hydroxide to start in it, OH in there, it's going to be a strong base. So this is showing us the relative strength of the different common acids and bases that we have. Notice the neutral is not necessarily in halfway, but the neutral, and then on the top are the acids, and then the bottom are the bases. So the farther away you get from neutral, you increase the strength of the acid or the base. So that means that something with a pH of like 1, if you had pH is equal to 1 compared to a pH of 6, the pH of 1 is going to be a stronger acid, so that means that it's going to break apart more easily than the pH of 6. Same thing, closer to neutral for the bases, so that means a pH of 8, so that's strong and weak, is going to be weak compared to a pH of 13. Would be strong because it's farther away from neutral. As you go farther away, it gets stronger. Okay, that's something that's just really good to know. Concentration versus strength. The words concentrated and dilute indicate how much of an acid or base is dissolved in the solution. They refer to the number of moles or of the acid or base that's in a given volume. That's why we use molarity usually to talk about concentration. The words strong and weak do not refer to this at all. They refer to the extent of ionization or dissociation of an acid or a base. So comparing concentrations and strengths. Well, for the first one, we have hydrochloric acid versus gastric juice, like what's inside your intestinal tract and in your stomach. They're both hydrochloric acid, in case you didn't know that. But notice how their concentrations are different. where we have 12 molar versus 0.8 molar. So the 12 molar is concentrated versus dilute for the 0.8 molar. But since they're both HCl, we classify their strength as strong. It doesn't matter their concentration, they're both going to be strong acids. Then we have ethanoic acid and vinegar. They are the same thing. Another way to say ethanoic acid would be to say acetic acid. That's what I normally say. But we have 17 molar versus 0.2 molar. So there again, 17 is concentrated and 0.2 is dilute. But since they're both from the weak category, their strength is going to be classified as weak. Okay, so this is just to show you how, no matter what the molarity is, even if it's a very high molarity, it can still be classified as strong or weak because pH is different than concentration. So the last thing that we're going to do are acid-base titrations, where we show a neutralization reaction. The neutralization reaction happens when you have an acid and a base react together to form a salt and water. So this is if you think back from chapter 11, the net ionic equation for a different kind of, for a neutralization reaction. Okay, so like for example, I have down here in my notes that this could be made from if we took like HCl, which is a strong acid, plus sodium hydroxide, which is a strong base, and it acts as a double replacement reaction. So the outsides make water, H2O, and the insides make sodium chloride. So this is our salt. Okay, there's our liquid water. And then this is our base and our acid. So we would get rid of the spectator ions here because the salt is going to be aqueous. And so then we'd be left with the hydrogen ion going with the hydroxide to make the water. Okay, so to analyze the acid or base content of a solution, we can perform titrations. A titration involves the delivery of a measured volume of a solution of known concentration, the titrant is what we call that, into the solution being analyzed, which is called the analyte. So we use burettes for this. We learned about burettes like on the second day of school or something when we started talking about lab equipment, but we just haven't used them yet, so here we are at the end of the year. A burette can help us give a very precise measurement. They're extremely accurate. Every tick mark on there is 1/10 of a milliliter, so we can know with very good precision how much we actually add. So we want to add slowly so that we know exactly how much is reached. We get endpoints and equivalence points here. The point when enough analyte has been acted to react with all of the titrant, they're equal. We call that the equivalence point. So at the equivalence point, it's important to know that the moles are equal to each other. So with our neutralization equation we just saw, we're saying at the equivalence point that the moles of the H plus are equal to the moles of the OH minus. So if you know the molarity of the hydroxide and you know how much you added, then we can do some math to figure out how many moles of H plus we had. And then that can help us figure out the molarity of the H plus. We do that a lot in AP chemistry when we reach this equivalence point. The end point is when the indicator changes color. So we talked about indicators briefly before, but indicators change colors when they reach different pHs and when they're detecting different amounts of H plus or OH minus in the solution. So when we're using phenolphthalein, we are going from clear and colorless to pink. And so this is showing how a good endpoint would be this light baby pink color where you can barely tell that it's pink versus the fuchsia, magenta, hot pink mess over here. So if you go with the hot pink, that means you overly titrated, and so your calculations are going to be off because of that. So you want to go the light baby pink that doesn't go away when you swirl it, but it's barely there, so then you know you reach the true endpoint. So for example 7, we're going to do a calculation that will be very similar to what we do with our last lab activity when we actually get to use the burettes and do a titration, where we have to remember that the moles of the H plus are equal to the moles of the OH minus. Okay, that's going to help us out immensely. Okay, so a 25 milliliter solution of H2SO4, which is sulfuric acid, is neutralized by 18 milliliters of a 1 molar solution of sodium hydroxide. What's the concentration of the H2SO4 solution? Okay, well, let's think about what we've got here. Okay, all of the H plus information is going to be coming from the H2SO4 because that's our acid in this problem. And then all of the base equation, or the base information, or the hydroxide information, is going to be coming from the sodium hydroxide. Okay, so let's, and remember, like, I have to write a little bigger here for these examples, so make sure that you're leaving yourself plenty of room to do the math. But let's figure out what we have for each so that we know what we have to solve for. Okay, well, we know that we have 25 milliliters of the H2SO4, and we have 18 milliliters of the NaOH, and we know that it's a 1.0 molar solution of the NaOH. So we want to know the concentration of the H2SO4. So the concentration of that is actually the molarity of it. So we want to know the molarity of the H2SO4. Okay, so what we will need to do is, this is super important, right? If we can use this information to find moles of OH, then we can figure out the moles of H plus and then go find the molarity. Okay, so let me clear my screen so I have some room. Remember our molarity equals moles over liters equation from back in chapter 16? Well, I'm going to go ahead and plug in my information from the sodium hydroxide. So the molarity of it was 1.0. I don't know the moles, so I'm going to throw an X for moles. And I did know that it was 18 milliliters, but I need to change that to liters, so it's going to be 0.018 liters. Sorry, that E looks terrible. Okay, so remember how we solved this? We cross multiply, right? So when we cross multiply, 0.018 times 1, so that is equal to X. And so that is our moles of the OH, or the sodium hydroxide, but it's the same thing here. Okay? So now that we know the moles of the OH, and we said the moles are equal to the moles, that means that we also have 0.018 moles of the H plus. Okay? Well, the only thing that's tricky here is this 2 on the H2SO4. Because it has a 2, that means that the concentration, or the moles of the H plus, are times 2 versus the moles of the H2SO4. So that means that the moles that we just found are actually twice as much as the moles that we need for our H2SO4. So that means we have to take the 0.018 moles divided by 2. And when we do that, it's going to be equal to 0.009 moles, and that's now the moles of the H2SO4. Okay, so then last but not least, I need to clear because I'm out of room, we can use that to find the molarity of the acid. So now I'm going to take the 0.009 moles of the H2SO4 divided by the volume of the H2SO4, which is 25 milliliters, changed to liters. So it's 0.025 liters. When we divide that out, we get incorrect significant figures, 0.36 molar. and that's the molarity of the H2SO4. So this example is a little bit more complicated. If you would have an acid that was like HCl, right? There's only one H there. So that means that if there's only one H, you don't have to do that whole divide by 2 thing that we did. I just wanted to do a more complicated one in the notes so that if you got an easier one, life would be better. Ask me questions in class. This is the last video for the entire year, so good luck.